This is section 6.5. The title is Logistic Growth, but today in this first part we will not be doing logistic growth. We're going to be doing integration with partial fractions. Now we're going to use this eventually in the logistic growth. In example 1, we are finding a partial fraction decomposition, which means we're going to take this fraction, which has a quadratic denominator, and we're going to split it up into two fractions with linear denominators. That's the goal. We start out by factoring the denominator. It factors into 2x minus 1 and x plus 3. We're going to take this fraction and we want to turn it into two fractions with linear denominators. So x to the first, x to the first. So we set a over the first factor plus b over the second factor, and this will always be a and b. This statement is not necessarily true because we need a common denominator, and this denominator is much more complicated than these two. Well, we can get common denominator by multiplying the first one by x minus 3 over x minus 3, and multiplying the second fraction by 2x minus 1 over 2x minus 1. Now all three of the fractions will have common denominators. Now that we have three common denominators, we can ignore the denominators. And we'll have x minus 13 equals a times x minus 3 plus b times 2x minus 1. If all the denominators are the same, we don't have to worry about them. Our next step is we're going to let x equal 3, because that is what will make this factor 0. That's what will eliminate the a. And we can pick x to be anything we want under the sun. In this case, we want it to be 3 so that a is eliminated. Now, if x is 3, then we have to put 3 in for every x that we see. 3 minus 13 is negative 10. 2 times 3 minus 1, that's 6 minus 1, that ends up being 5. So negative 10 equals 5b. b ends up being negative 2. And if we let x equal 1/2, that's what makes this factor 0. Then a ends up being, let's see, after a little bit of algebra, 5. Now we put those, did I put those values back in? Yes, I did. So, what is it called? The sum of rational functions with linear denominators is 5 over 2x minus 1 minus 2 over x minus 3. And that's what the instructions wanted us to do. Let me cover up some of this so you don't get overstimulated with all this. Let's ignore number 8 for right now. Like this isn't enough to look at. We're going to evaluate the integral, and we have this denominator that's a quadratic. And if you take the derivative of x squared, it's 2x, and the derivative of x is 1. And if we have 2x plus 1 as the derivative, we're not going to be able to set up a u substitution here because 2x plus 1 is not even close to 2x plus 16. And you'll see what I mean later in the presentation. So we're going to do this by partial fractions, is what this is called. Our first step is to factor x squared plus x minus 6. That factors into x plus 3x minus 2. Next step is the common denominator. And once all the denominators are exactly the same, all we have to do is worry about the numerators. If we let x equals 2, that's what makes this factor 0. We get b to be 4. And if we let x equal negative 3, then a is negative 2. If we put the a and b back into this spot right here, then we have negative 2 over x plus 3. Negative 2 goes in for this a. And the 4 goes in for the b. So we have 4 over x minus 2. So 2x plus 16 over x squared plus x minus 6 is the same as this right here. We eventually want to take the integral. That's what we're trying to accomplish, evaluate the integral. Well, now that we have linear denominators, we can take the antiderivative of these. So the antiderivative of the original is equal to the antiderivative of the individual fractions with linear denominators. Now, we can take out a negative 2 here, we can take out a 4 on this one, and the antiderivative of 1 over x plus 3 is a natural log of the absolute value of x plus 3. And then plus c, of course. If we rearrange these two, then I can bring the 4 up and bring the 2 up to the power And because these are even powers, I don't need the absolute value now because there's no chance of this being negative. And using the properties of natural logs, we have the answer right here. In number 8, there's a little trick we can use. Notice how we have an x to the first over x squared. And if you have the denominator's power is 1 more than the numerator's, well, we just use partial fractions. But if the powers are exactly the same, you can reduce your work on this one by doing a little bit of long division. I know how we love long division, but don't worry, this is really a one-step problem. And we're going to take x squared minus 6 divided by x squared minus 9. And we're going to do that with long division. How many times does x squared go into x squared? 1 time. So we have x squared minus 9. And in long division, we always subtract. So negative 6 minus negative 9 is a positive 3. So what we've done, we've changed this problem from what you see here to 1 plus 3 over x squared minus 9, which it's like a mixed number except with a variable. Now we're going to do our partial fractions. We're going to factor the denominator. I'm going to ignore the 1 for right now, and we're just going to do the partial fractions on 3 over x squared minus 9. So we have a over x plus 3, b over x minus 3. Doing common denominator and then ignoring the denominators, we get this line right here. We'll let x equal 3. That gives us b to be 1/2. Let x equals negative 3. That means a is negative 1/2. Now I know this is a complex fraction when we put these a's and b's back in to here, but that's okay. You don't really have to worry about that because we're going to pull the negative 1/2 and the 1/2 out front of the integral when we take the antiderivative anyway. So the antiderivative of 1, now this 1, remember, comes from our long division. The antiderivative of 1 is x. I can pull the negative 1/2 out, and the antiderivative of 1 over x plus 3 is the natural log of the absolute value of x plus 3. And we do the same thing for the third term here. We rearrange a little bit. 1/2 powers are square roots, so you end up with the following answer. And that is number 8. Next one, I thought we'd look at number 18. It's a long division problem again. We're going to take 2t to the third divided by t to the third minus t. And we're going to do that because the powers are exactly the same. If this was an x squared, then I would just do partial fractions. How many times does t to the third go into 2t to the third? Well, 2 times. So 2 times t to the third is 2t to the third. 2 times negative t is negative 2t. We need a 0 so that we can match up the t's here. This top doesn't have a t, it does a t to the third. And in long division, we always subtract. So negative 0, well, 0 minus negative 2 is 2. We can turn this 2t to the third over t third minus 1 into 2 plus 2t over t to the third minus t. And with a little bit of, we can factor out, a little bit of factoring here, we can factor out the t, cancel it out, we get 2 over t squared minus 1. And then we can take the antiderivative of 2. Antiderivative 2 would be 2t. But for the second part, the other term, we're going to need partial fractions again. So we factor a over t minus 1, b over t plus 1. Common denominator, let t equal negative 1 and t equal 1. b ends up being negative 1 and a is 1. We plug those a and b's back into their respective places. We get 1 over t minus 1 minus 1 over t plus 1 because b is negative 1, and do a little bit of anti-differentiation. We get 2t plus the natural log of absolute value of t minus 1 minus natural log of absolute value of t plus 1 plus c. And here's your final answer. And you can see I forgot to write the plus c. You should never forget your plus c on an indefinite integral. On the very last one that I want to show you, number 20, it says find the integral without using the technique of partial fractions. This one can be done with u substitution because the derivative of 2x squared minus 3x plus 1 is 4x minus 3, which is exactly what we have here on the top. We can let the bottom equal u. 4x minus 3 dx ends up being du. Antiderivative is natural log of absolute value of u plus c. And since this is indefinite, we have to put the u back in. And of course, we have the plus c. And that's it.